theme is outline of integration theory. And in particular, Stokes' theorem. And where we are going, I don't know if I'll reach that today, but certainly tomorrow, to symplectic geometry. And Hamiltonian system. Anyway, I think it's good for you all to see a little bit of integration theory. So, a tool that is needed for integration theory, constructing the integral, I've spoken about this, but I want to repeat it, just to make sure you understand carefully, is what we call partition of unity. Remind you of this tool. So what is the situation? We have M as a manifold. And we cover M by open sets. I guess I would like to assume that they are relatively compact. And it's of course a locally finite covering. Now, one thing you can check, it's not difficult to check, you can shrink the covering. So shrinking is, let me just phrase it in rough terms first. The cover, you can shrink the covering, so shrinking is possible. Now shrinking means this, means that if you have one of these open sets, say UI, something like this, maybe this is UI. You can shrink it a little bit, all the UIs. Maybe I'll make the shrunken set a different color. So the shrunken set maybe looks like this. And that's, say, VI. Well, you can always do that. I mean, there's no problem. Anybody can shrink a set. Make it a little smaller. So shrinking is possible, where i.e. you have a covering V, VI, where VI is relatively, just exactly as I've drawn in here, where VI is relatively compact UI. I know in physics some of these words are not familiar, but it means that this thing is bounded inside of ui and bounded away from the boundary. I mean, it's just like it looks. Okay, so that's what I mean by shrinking. And the point is, you see, it's still a cover. That's what I'm claiming. It's still a cover. Yeah, so you make a little small shrinking and it's still a cover. Okay, you can imagine what this might look like. You see, if you have, for example, two intervals, this would be U1, say from here, and this would be U2 from here. And then, well, you see, I shrink a little bit here. Well, I have to have U3 here too. You see, I have U3 here. Yeah. So I shrink a little here, and I shrink a little here, and I still have a cover. Just a little shrinkage, you still have a cover. So you can prove that. That's of fundamental importance because this implies there are cutoff functions. I've talked about this before, I just wanted to re-emphasize it. There are cutoff functions, say chi I, which are smooth functions on the big ui, and they have the following property. First of all, with the following property, so let's go up here with the following property. It's easy to check. You have these functions. First of all, they're between, they lie between 0 and 1, so they're non-negative functions. And chi I is identically 1 on vi, and the support of chi I, where it's not equal to 0, is compact in ui. So near the boundary, these functions out here are 0. So near the boundary, they're 0. You should always have some picture in your head, at least I always do. Maybe near the boundary like this, something like this. Here, see here in vi they are identically 1, and they lie in between 1 and 0, but here the chi's are identically 0 near the boundary. Cutoff function. We've talked about that before. 1 here, down, cut. Okay, so this exists, and then you do the following thing. You make some crazy function, so crazy function. Namely, you add up all the chi i's. You add them all up. Okay? Now notice, that's finite because its covering has been assumed to be locally finite. So every point is only contained in finitely many sets. It's finite, so there's no question of convergence here. Second of all, this thing is obviously positive everywhere because it's 1. You see this function is 1 on the v's, and the v's still cover. So it's bigger than 1 actually. It's bigger than 1. Well, let me just write that here. Well, it's probably, okay, bigger equal 1. Okay, it's some crazy function. I have no idea what this function looks like. I mean, it must be horrible. But it's smooth. And maybe let's call this function f. And then what we do is do something silly. We say gamma I is equal to chi I divided by f. And then you make the silly observation that the sum of the gamma i's is identically 1. Because we scaled the function and we're okay, right? So that's a partition of unity, right? The individual functions, gamma I, well, they're just the same as chi except scaled. That means the gamma i's are something here and are cut off and so on. So that's what we call partition of unity. So this collection here, gamma I, is called partition of unity. Sometimes we just write partition 1 because it's 1 and we partition it into a sum of things. Okay? Very useful thing. I should comment that this was first written down as far as I understand it, in very, very late in mathematics, in 1948, by whose name? He realized that you really need these things, and so he really constructed these partitions of unity. Very expensive. So that's that. Okay. Now, we're going to construct the integral. So what is an integral? It's something very general. First of all, you see, when you grow up in mathematics, you have these basic courses in mathematics where you worry about an integral converging, right? So, in your past, then some teacher asked you to integrate this thing, and you said, okay, you put that there, but you don't know what it means because you didn't know what a differential form was at the stage of the game. So you wrote that down there, and you say, well, I don't know what this thing is. This is what is this? This is an integral form. This is log x evaluated from 0 to 1, and this is infinity. Right? Right? Log of 0 is minus infinity is infinity. Well, then you worried about that and so on. Right? You worried about that. So I don't worry about it. Then somebody else says, well, you can have fun. You say you can still have it blow up, but then this is more or less, except for some number, maybe let me even try to get the number right. You tell me this is 2 square root of x evaluated from 0 to 1, is that right? Yeah, you differentiate, the half comes down, kills the 2, and you're having fun. And so and you're so incredibly happy because you told your teacher the number is 2. Right? And then we in mathematics, or not me because I hate this, but we in mathematics have big trouble because of the internet and because of tables and because of numerical procedures and all sorts of stuff. You just go integral from something to something, something to something is something. You don't care. And you never knew what an integral was in the first place. So what an integral is a functional, a linear functional, from smooth functions, not functions, n form. So from now on, just keep this, the dimension of manifold is n. To the real numbers, everything over the real numbers at first. And of course, this is a one form, right? I mean, dx is a one form on one dimension, right? One form, one dimension, n form, n dimension. But the problem is that blows up maybe, so there's no way we should try to do that, so we integrate forms with compact support. Okay? So I put that little, nowadays with text and so on, we can write all sorts of indices. So I mean with compact support. Okay? Outside of a compact set is 0. Right? This is fundamental. Because then you have no problem at all with convergence of anything. Okay? This is the first thing. So we're integrating smooth objects with compact support. Keeping in mind, all other integrals arise from these integrals by completion. Understand what I'm saying? You complete this integral someplace, just like you complete the real numbers. You may have learned you integrate step functions or something like this and then complete. Well, it's the same thing, you complete. Complete. Everything's complete. Right, that's the way you do it. But here, I will complete because I don't care. I'm only interested in integrating smooth things. Okay, so there's nothing subtle here, just smooth. I don't care piecewise smooth. So this thing, of course, should be linear. Sorry, my didactics have gotten poor here, but so you can see this, maybe I'll just only go up to here now. It's too bad I'm so short. I could stand on a chair. So it should be linear. As a linear function here. Of course, over the real, this is a real vector space over the real, so it should be a linear thing. And there's only one property of the integral. There's exactly one property of the integral. Punkt, comma, aus. So I will write here a symbol, because you see, just to remind you that it has to do with m. If you have another m, then you have another integral. So, okay. So it's linear with precisely one other rule. So linear plus transformation rule. You remember, sometimes you call that the substitution rule. I think I talked about it last time, right? Right? But now we have to be careful about that, because if you remember, at least I always mess it up and make a mistake with substitution rule. You know, you're integrating from 0 to 1, and then you make some change of variables so that 1 becomes 0 and 0. You know, you do that, and then, right? And then you make a sign mistakes, right? Because something, yeah? You understand what I'm saying? That's interesting. You might make a, let's just draw a picture of a transformation. So you make a diffeomorphism of the interval. So the interval, let's say, let's have some fun. This is fun. You know, in Germany, I have to write fun on the board so people realize we're having fun. But here, are there any Germans in this audience? I don't know. So let's try this thing, and right, a diffeomorphism. So you want to substitute a diffeomorphism, right? And so you say, well, okay, everything's cool. This integral, the integral f of t dt should be made an integral of f composed with phi. Some people like to write s, phi prime of s ds, right? Right? I mean, that's, everybody writes that. Then one forgets that one has made a mistake, because this change of variables from 0 to 1 maps 1 to 0 and 0 to 1. It could be like this, right? And now you have to change the integral around and make a sign change, right? You know all this, because you do this in 8th grade, right? Right? And I've made many sign changes, mistakes, as you know, in my life. Here. Okay. So the problem with this guy, you see, it changes. Say this is high, this is 1. I mean, this is phi, and this is 1. Maps 0 to 1 and 1 to 0. It's better to write it like this. Here you go from 0 to 1, and this phi goes backwards. Right? It goes backwards. Phi reverses the orientation. Phi reverses the orientation, right? And if you don't watch out, you'll make a sign mistake. So all of this integration theory has to be done in the context of some orientation. Okay? Otherwise, you're going to make a sign mistake. That's all you're going to make is a mistake, but it's going to be a sign mistake. So an assumption in the whole theory, and I mean, I said an integral is linear with transformation rule, is this. So the big assumption to make this stuff go through, at least for me, and I need this assumption, is that m omega is an oriented manifold. So it's not just a manifold, I choose an orientation, just like on this thing here, we have this orientation, is given by dx, right? Not minus dx, right? You have two forms, dx and minus dx, right? And one has one side, one has the other. So we fix the orientation to discuss it. Everything will be done in the context of orientation preserving. Okay? Okay, so the transformation rule now is you have an integral from, let's call this Vn. So we have a diffeomorphism now from n to n, which is orientation preserving. So then integral over n of something, say, say over n of something, alpha, is the same as integral over n of pullback. Okay. And pullback, as you know, will be the transformation rule, right? Pullback of in coordinates, dx1, dx2, and so on, you get the Jacobian. In this case, positive Jacobian. This is the question. You see, if you have the wrong orientation, it gets, right? Jacobian can have two sides. So here, in some sense, the thing that you have is the absolute value of the Jacobian, which is positive. Right? In some sense, you can think measure theoretically. I mean, you're pulling back a positive measure to a positive measure, something like this. Okay. So this is the statement. There is exactly one integral with this property. Okay? That's it. There's exactly one integral with this property. The property is, it's a linear functional on the forms of compact support, and transformation rule is that. It's easy to see uniqueness, but you have to construct it. Okay? And so I will construct it for you. So, construction. Well, the construction is completely trivial, except for one point, the transformation. So, let's just, how would we do this? So, we want to construct, we let ui be as above, so in the preparations, and gamma I, a partition of unity, as above. Okay. Then the integral over m of alpha equals the sum of the integrals over I of m of gamma I alpha I. And the integrals over m of gamma I alpha I is the same thing. This step here is trivial. This is the same because the support is in ui. This is no problem to check. It has to be there. So of gamma I alpha I.
Should be ui or vi here?
Say it again, please.
Is here ui or vi?
Who's speaking? I'm sorry, I guess. Yeah.
Is it vi or ui?
Ui, the big set.
But our support is defined on vi. Why it becomes ui again?
Maybe I made a notation mistake here. I constructed this partition of unity using the VI. Yeah, it was the individual functions were 1 on the VI, and then they came down to right. And then okay, yeah. Now, so the question is then. The question is what about how to integrate something like this? So the question is how to define. How to define the integral over ui, such an integral. So I have localized the question. I've localized the questions as small as I want. I've localized the question as small as I want, yes.
Do we know integration on our end?
Exactly. So
I mean, do we
you're going to make the right suggestion, I think. Go ahead, yeah.
We just go to our end and see what's there.
Yeah, so this is very good. So I'm going to write just formally what Mihai just said. So what we need to do then is this is what Mihai is suggesting, is we take a cube W, maybe even a fixed one. This is a cube in Rn. That's what you mean, which is a coordinate cube. So let's say phi Ci into the manifold. So if it goes in here to the manifold someplace, we'll take that to be Ui. So we will cover the manifold by what I will call cubes. I mean, they're abstract cubes, these are diffeomorphisms, so they're coordinate cubes of that type. And that's what your idea is, just pull it back to Rn, this is a cube in Rn, and integrate. So the integral over Ui of some form, it doesn't matter what it is now, with compact support in Ui, I'll just call it beta, will now be defined to be the integral over the cube of the pullback of the form to the cube. That's what you had in mind, I think. Right? Just pull it back. It has to be, because transformation rule, it has to be correct, because that is the transformation rule. Now, what does the transformation rule say? You need orientation preserving. So you better pull it back with an orientation preserving diffeomorphism. So the condition here is that this thing is orientation preserving. So what Mihai had in mind, I think, is that we view W as equipped with the standard orientation of Rn. So we will use, this is what I always call the standard orientation of Rn. So the standard orientation of Rn, right? And now, so all we need to do now is define, and everybody has in mind how we should define it. We need to know how to define the integral of, say, a form. Well, a form is a function times such a thing over a cube, and the notation has been chosen to work. Okay, and this is the repeated integral. Okay, so this is the usual repeated integral. You notice I don't need to write all those integrals. I mean, I can't believe all these books. 3 integrals, 7 integrals, 25 integrals. Yeah, that's great. Probably could get some computer science freak to make a program for tech. We integrate over 85-dimensional space and push one button and get all these integrals across. Okay, so everybody knows how to do that. Yeah, everybody knows how to do that. So it's been done. So that's the definition. So let me just write it again. The integral of, I'll write it again in short language. The integral over n of form alpha equals the integral over the sum times the pullback of these coordinate things, partition of unity alpha over cube. That's it. It has to be that. We're forced to do that by this law that the transformation rule is going to work. Right? You see, I just use the transformation rule here, that's all. Okay, so that's a good definition, except it depends on the covering, it depends on the partition of unity. I don't know what else it depends on. It's really, really dependent. And now theorem, and of course, this theorem has to use the transformation rule on cubes. It has to use the transformation rule on cubes. You all know it. The Jacobian comes out as determinant and all that. So, but this theorem, using that and a bunch of fooling around theorem, the integral is well defined. So anyway, you want to cut this thing up with partition of unity and coverings and all this stuff, it's well defined. Okay? That's great. So of course, I'm not going to prove that. It takes, take half a lecture to prove it because you have to be rather careful. and it's written down beautifully, by the way, in volume 1 of Spivak. I highly recommend these books of Spivak. Volume 1 is, they're called differential geometry or something, but volume 1 is just basics like this in Spivak. So I always quote Spivak to perhaps also his book on Calculus on Manifolds. So the integrals. Okay. Now, that's okay, but it's not enough. So we need an integral. The following, an integral of a volume of a form again, top dimensional form, over D, where D is a relatively compact domain in the manifold, and I don't assume that this has compact support. It could go out to the boundary. I mean, I want to be able to integrate that. For example, maybe not that. I mean, that blows up at the boundary. I hate it. But at least something that's continuous to the boundary, right? I mean, I want to be able to do that. I want something reasonable like. So I want to assume that this, so if you're, just keep in mind, for those of you who don't like this notation, compact support, here's the manifold D, M, and a domain like this looks like this, and I'm assuming now that the boundary is smooth. So that's the setup that I would like to discuss. An integral over a domain. Well, for example, I'd like to discuss an integral over a ball in Rn, whose boundary is a sphere. I mean, come on, or an ellipsoid, the inside of it, whose boundary is this, whatever you call this thing. Right? I mean, it was very important. And I don't want to assume that this has compact support in D. I want that this thing has really boundary values. You badly need to handle boundary value problems. I mean, everywhere in the world you have boundary value problems. Okay. So this thing is not necessarily, so what, yeah. So the assumption on alpha is that alpha is smooth with compact support in M. So I want to, the same old thing. So alpha lives on M. I don't care, maybe, at least you see, if I just say it's defined, it has compact support and it's defined on M, I mean, what I can do, and I will do this always, I can always cut off its support so that its support is very, very near D. I will tell you how to do that. I can always assume that the support of alpha is arbitrarily near D, and I'm going to show you how to do that, okay? But again, you give me D, should be a smooth boundary. I want to integrate a form that's defined a little bit further than D. I don't care where. It's just so that it's defined. So it's defined in the neighborhood of D. Right, and D, and the boundary of D should be smooth. Okay. And now there are two theorems in basic mathematics and analysis. One is called the rank theorem, and the other theorem is called Stokes' theorem. There are only these two theorems. And now, what is Stokes' theorem? Well, let's write the theorem. The integral of D, some D of some form, I don't know, mu. I'm going to write it in a sloppy way, and then I'm going to make it precise. D mu over D is equal to mu over dd. This is Stokes' theorem. And all of you who see these various things like curl, rot, gradient, and all these things, and you see these versions of Stokes' theorem, you will prove all of these theorems from this one theorem. Okay? Every theorem you know is Green's theorem. All theorems you know are contained in this. Yes, you have a question.
Professor, what is mu here?
Mu is an n-1 form. Because we have to have an n form to integrate it. Okay, but thank you for, I just didn't write it. So, mu is an n-1 form. Okay, let me just say it's defined on the closure of V, so to make sure it's just defined near, just so you cross the boundary. I mean, that's all I care, yeah?
So now we only work in spaces where the last Durand cohomology is 0 because...
No.
But how do you integrate things that are not exact?
Say it again?
How do you integrate things that are not exact? Because you can only integrate things that are exact here. Right?
No, I didn't say I could integrate things exact. None of these things are exact here necessarily.
No, but in Stokes' theorem.
So Stokes' theorem says that if you have an exact form, this is how you do it. You can integrate anything you want. Okay? Yeah, but this is a statement about exact forms, if you like. That's what.
Yeah.
That's right. Yeah, thank you. That's a nice formulation. This is a statement. We're discussing integrating a form which is exact over D is the same as a boundary integral. You push the integral to the boundary. Yeah? It's a very, very powerful tool. You see, and there's the mathematicians, this is probably physics influence. You see, this D and this D are related. Okay? You have to think about what that means. Those two D's are related. For those of you who have a little bit of experience, this D in Durand cohomology, I'm glad you brought it up, is somehow dual to D in homology. You see, this is the boundary in homology here, and this is the boundary in Durand, and this is the duality between Durand cohomology and homology. So that's just for people who've had some experience in this matter. It's not important. Okay? Now there's some things missing here. So I'm glad you mentioned all these things you all mentioned. The one thing that is necessary here, I made big mouth about all of this stuff. I need an orientation. Right? I need an orientation on the boundary. Right? Otherwise I can't integrate. Right? Every integral I write down on a manifold, this happens to be a nice boundary manifold, needs an orientation. So there is one gap that I need to discuss, and that's the orientation on the boundary. And this is called the induced orientation. I need to talk about that, otherwise I don't even have an integral. And there's another gap. It's really not a gap, it's just a gap in notation. You should be very careful. This is a form on M. So mu is a form on M. And I'm integrating it over the boundary. Now you can't integrate a form on M over the boundary. You can't. It's defined on M. It's not defined on the boundary. Okay. So I warn you, every time you have a submanifold, the boundary is a submanifold here, right? Every time you have a submanifold, don't write restriction, always write pullback. Okay? So we have a pullback, we have an injection, canonical injection of the boundary into the manifold. Right? This is put it in the manifold. And what we're dealing with here, this integral here is really the integral over the boundary of the pullback of mu to the boundary. You can call it restriction if you want, but you will get in big trouble if you start restricting forms instead of pullback. Always write the map that you have. The map in this case is just the map of the boundary in there. And you just pull it back to the boundary. Okay. So that is what I mean by this. Many people write this thing because it's so beautiful, but actually it's the pullback of this form to the boundary that you're really dealing with. Okay, I want to give you an example of that. I'm going to tell you I'm going to tell you about both. I'm going to fill both gaps now. So let me see here. The first gap I should fill first, I think. And so let me just do that in some detail. So a little segment here on the so-called induced orientation. Of the boundary. In some sense, this is slightly non-trivial now. So the first thing is we have a domain D. And I explained last time that it can be defined by a smooth function, f being less than 0, so f being a smooth function on the manifold. Okay? Remember how maybe I didn't talk about it in detail in class, but locally it's true, that's almost definition. It's locally just smooth function, and then you paste these smooth functions together with a partition of unity around the boundary. So you can assume that it's defined by a smooth function, and where df is not 0 near the boundary. So that's smooth defining function of the boundary. Recall that's how we really define this. That means locally, this is now globally, but locally using the theorem of rank. Locally you can map this, say this is point P0. You can locally map this then using the rank theorem to, let me use the color scheme again. Using the rank theorem, you can map this piece here to a coordinate, hyperplane. That would be the first coordinate, for example. First coordinate equal to 0, and this is the part. So the function f is somehow transported over to the first coordinate, and then this thing gets mapped into here somehow like that. Right? That is the definition of a smooth boundary. Boom. Okay? And then you glue these smooth things together around the boundary and you get a global defining function. Okay? That's a fundamental tool in this subject. This course is called Mathematical Foundations of Mathematical Physics. These are tools for mathematics. The fundamental tool, you have such a defining function. Okay, and now what I want to do is I want to understand what it means going from inside to outside. Yeah, I want to go, so it's a beautiful day. We are in this classroom and we're inside and we want to know how to go outside into the sun. So how to go from inside D to outside D. Okay, so that's the idea. Somehow you want to go from inside to outside. Well, we've talked about this. You introduce Riemannian metric, and if you have a metric, you can transport D of a function to gradient. So introduce, it doesn't matter what the metric is, a Riemannian metric. G on M, doesn't matter where, you have plenty of them, I construct them plenty. And then if you have this, then df gets transported to the gradient of f, I write here with respect to g. Remember, it depends on the metric. Okay? However, the gradient flow of this function is from inside to outside. You understand what that means? The gradient flow is from inside to outside. What does that mean? So the gradient flow of the gradient. So the gradient is a vector field. The vector field is locally integrable. You follow along the curves of integration with time t. There's an obvious orientation of time t, from t going from plus to minus, that orientation, right? It means that the function f is increasing along the integral curves of this gradient. This is fundamental. Another way to formulate this is this. If GT is the one parameter group, it's the local one parameter group of this field, of the field, then if you differentiate the function, by pushing it along these curves. So here is D, and say we start at the boundary, here's P, and now you push along an integral curve with the local one parameter group. This derivative is positive. That means the function is increasing here. It's increasing along that curve. Okay? No. This is really, really fundamental. Yes. You have a normal vector field. The normal vector field is the gradient vector field defined by the defining function n sub metric. Okay? You see it in every course you take in applied sciences. You see Green's theorem and all of this nonsense with the normal thing. You've seen this, right? The normal, the tangential, S, it's called always, and N. Right. This is it. Okay? It's going from inside to outside. Okay? So this vector field is canonically defined and goes from inside to outside. And now the induced orientation is contraction with respect to this gradient vector field of the orientation well, this is contraction of the orientation omega pulled back to the boundary. Okay. You have orientation on the big space. I'm going to do an example so you become happy. But you have an orientation on the big space, right? You have a defining function that defines the domain, right? This function has non-vanishing, you see, that's the key issue here. This function has non-vanishing differential. By the way, otherwise it's a horrible function, right? Because of that, you can apply the rank theorem, and that means it looks locally just like a half space. Yeah. But not only that, if you introduce a metric, you can have the gradient flow. The gradient flow depends on the metric, of course. We know that. But the fact is, it flows from inside to outside because this is always true. So its orientation is the same, no matter which one you chose. Yes?
Is it going outside because inside is the function is negative? And
That's right. Outside is positive. That is
that's why?
That's all. That's all.
Mhm.
Well, and the flow is oriented in the same way. I mean, right? The flow is.
Yeah, it should be.
Yeah, it is.
Professor, why do we define the inside to be negative? Could we also define inside to be positive?
Absolutely right. I don't know if you heard his question. He said, why do we define inside to be negative? It's sort of a positive thing to be inside, except on a day like this. Right? But in Germany, you're right. In Germany, northern Germany particularly, it's positive to be inside. You know, in some place in Fiji Islands, it's positive to be outside. So maybe, I don't know. The point is, there might be reasons, but just let's take example after example after example, where you see that sign will be sort of the negative sign, the natural sign. But you're absolutely right. It's just a convention. Okay. Let's do an example. And then compute induced orientation. By the way, I somehow learned, particularly with physicists, if they use a certain notation, I copy it. Because they somehow have thought more about this stuff than I have. And so certain things like this, I just tend to copy the notation. I'm not very creative there. I save my creativity for other things. No, but physicists are very good with notation. The notation somehow reflects what's going on. By the way, another answer to your question, let me answer your question in another way. If you draw a circle, okay, and everybody tells you in complex analysis, when you make a residue, you integrate it like that, right? And the whole thing is they say, now you just walk around that circle and keep the domain on your left. Right? They're talking about that stupid remark. Okay? Well, look at this. Okay? Okay. This orientation here is fixed somehow by choosing the orientation going out here. You understand what I'm saying? You will have the normal field and the tangential field should be a positively oriented pair. You know, it is a positively oriented frame of R2 that you're going around the circle, sticking your hand out like this and going around like this, right? This is a positively oriented frame in the standard orientation of R2. It's a question. It's again. You have to. Where do you start? I mean, it's the chicken and the egg thing, right? I mean, where do you start? The way you start here is the standard orientation of R2. Okay? On the other hand, I can tell you, I know in Hamiltonian systems in physics, actually the flows go the other way. It's amazing. You know, they go this way around the circle. I hate it. But you just have to watch out. So I want to do an example maybe that might help you out. So I think if you take the unit ball, the ball of radius 1 in Rn, so x in Rn, such that norm, now here you go. Yes, you see, there's the function. Well, okay, I'm sorry. I know you guys are precise, but yeah. This is a defining function for the ball, right? Norm minus 1 less than 0. Did I do something terrible?
You wrote equal.
Yes, less. You paid attention, thank you. So this is, say, we draw it in dimension 3. So it's somehow inside the ball, inside here, this field. So let's say this is the n-dimensional ball in R. Right? let's compute the induced orientation form on the ball. In your physics courses, you will call this in R3 dA. You understand that? You see dA, integral something something dA. This says d of area. This is what is meant by a, area. But area, dA means in some sense canonical induced orientation form on the sphere. So we take the usual metric, and we take the normal field here of like 1, for example. So what is gradient here? Gradient here of f. So f, what is that? F is this function. So what is that? That's some, maybe, you want to know why physicists put a half here? Because when you differentiate, you kill the half. So, right? So df, if you kill the half just right, is this. Right? Remember, df is x dx with a half probably. But then you dualize to get the gradient. Right? And you drop and you exchange dx for ddx. So that's what that is. That's the gradient field. Okay? And now the volume form, so the induced orientation form is we contract with df, with the gradient, to form dx1 wedge dxn. Okay, so I have to contract this form, this is a sum here, contract this form into this form. Okay? Now, you know what that means. Remember what contraction means. Contraction of a form with a field is you put the field in the first entry. Right? Now here's a mistake. I put the field in the first entry here. Right? dx1. You see what I'm doing? I'm putting it in the first entry there. And dx1 picks up x1, right? Because dx1 is dual to ddx1. Yeah, but that's not a tensor, that's an alternating tensor. That means you have to alternate all the way through it. So you have to bring dx2 to the front, etc. You see, and you get the alternating thing, right? So I think I will convince you with this little remark that up to my usual sign mistake, I think this is probably this is probably this thing. Okay, and that is the induced area form on this field.
Don't you need also an n factorial somewhere or something?
What?
You need an n factorial somewhere or no?
You're saying you want some factorial in front of it? Something
You
like,
need it or no?
Factorial.
is that right?
Yeah, that's how we define the wedge in linear algebra.
Yeah, well, maybe, but it's whatever you want. I don't care about constants. Okay. So. So that's the induced orientation. Okay, that's a good example. So that's the induced orientation. And as I said before, I guess I don't have to discuss much more. This is just the integral of pullback. So now I have to prove for you Stokes' theorem. No problem. Okay. So, first of all, I need to define the integral. I need to define the integral over d. You realize it's not yet defined, right? Because I've only defined it on m, and and remember, I just defined it on m with compact supported functions. I haven't defined it on d at all. Okay? So here's what we do. I can make this precise later if we have time. So let chi n be a cutoff function which is identically one, in a neighborhood of D with support, so where it's not 0, let's say UN converging to the closure of D. I'm going to cut off this function, this form. And you get what I'm saying? Maybe not. So I have to draw you, remember my African student couldn't believe I drew this. He wanted this precise picture. And I have to draw it on a line. So here's D. This African student from Cameroon, a great guy. He turned out to be wonderfully successful. I just love it. So here's D. And here's chi n. It's 1 on D, but then its support is just a little bit bigger, and its support converges to D. You don't like it, I can tell. Do you get what I'm talking about? No?
Support converges.
Yeah, what it means is, yeah, what does it mean?
Intersection of all UMs is the closure.
Yeah, that's the best way to say it. What you guys are saying is the best way. Just the intersection of all the supports is D. Closure of D. Right? So obviously this is a stupid thing, everybody sees it. It converges to the step function, which is identically 1 on D and 0 outside. But it converges to something that's highly discontinuous. Right? Okay? But it's very easy to check that limit n goes to infinity of chi n over m alpha exists and is independent of the choice of chi n. Now I'm going to tell you how to make, watch me, and I'm going to tell you how to make chi n. Okay? Here's D, here's the gradient flow. You see it going outside? Okay? I start with a function that is 1 here near D, and as time increases, I move it down. Right? And as time increases by epsilon n, I've already killed it. So you see how to do it. So it's just something cutting off by time. You see, this is the time axis, and here at time 0, okay, it's still great, it's still wonderful, but then it comes down here to something like 1 over n. At time 1 over n, it's already died. So yeah, you push it, and at time 1 over n, it's already dead. Okay? That's the easier way to compute this with this so-called gradient flow. So that's that. That's that. Okay. And now I have to prove Stokes' theorem for you. And again, it only works because the integral is well defined. And that's always the hard part here. The rest of it is formal. So I'm going to take a very special covering of the domain D by special open sets where you will immediately know how to prove Stokes. So here's D, and remember I have to define, so what I've got to do, I've got to define this darn thing, so I really have to take a covering here that's reasonable, and here's the way I do it. I take, so M is the blackboard, so M is equals blackboard. So out here I take some covering, I don't care. I don't care, because I'm going to cut this thing off anyway out there, right? And in here, I will take some covering, I don't care. Because it's just, I'm not near the boundary. But the boundary I have to watch out for, because I want to prove Stokes theorem. So what I do is, at the boundary, now remember, this is not difficult to do, because I'm glad I still have this thing here. Locally, really, this is diffeomorphic to this picture here. So I can put beautiful cubes here, well, I'll draw them here now, say here, of the following type. So that looks like that. So this will be a covering of a neighborhood that's good enough, because the rest of it, the thing, okay, we have these things out here and so on. That I only need a neighborhood here because the form is 0 except very near here. So the key is at the boundary here, we have cubes that when this support contracts, only play a role in here. Okay. Now watch. Integral over n. Okay. Of now chi n. So alpha. What not alpha? D alpha. I'm sorry, D alpha. So I'm sorry, I'm going to cut it off in here. Chi. Stop. I want to get in a hurry here. So I'm going to suppress this limiting process here, and I'm going to leave that just up to you, where did it go? I'm going to suppress this limiting process here. I'm just going to integrate here over this stuff here. So the integral of D, here we go, D alpha equals the integral, and now I use partition of unity for this covering, over D, sum of the partition of unity, D, I don't care, gamma I times alpha over I, for these orientation preserving things. So sum over I, integral over the cube, right? Ci of D of gamma I alpha equals, so far everybody's happy. Okay, sum over the cube, this is I equals some finite number now because it's a finite cover. I equals 1 to n. D commutes with, this is pullback. D commutes with pullback. D, C, of gamma I. Well, maybe I don't want to do this yet. Let's have some fun. Let's do this out. C, I, you're going to get really excited with this. D, what do you call this rule? You multiply a function times a form. what do we call that? Leibniz rule, right? So d of a function times a form, let's do it out here. Let's have some fun here. First of all, d phi alpha plus, so I'm going to put an integral here, w plus, somebody have a complaint? Gamma I d alpha. Okay? Any observations here? That is a sum. This sum goes inside here, right? Right? What's the sum? What is? Any ideas about what that is?
1. It's 0.
It's 0. This is fantastic. You see, this partition of unity plays no role in this whatsoever. Okay. So what? Okay. Over W. So let me just write it out again. This is the sum over I equals 1 to n of the integral of this orientation preserving guy, partition of unity, what am I doing here? Everything I've said here is true, but what am I doing? Do I want to do this? What I have here is d alpha.
Are you applying Leibniz rule? Are you applying Leibniz rule here?
Am I what?
I mean, from the third step to the fourth step, are you applying the Leibniz rule for?
I'm applying the Leibniz rule from here to here.
Yeah. But should it be like d gamma I wedge d alpha in someplace?
Yeah, but well, you're absolutely right. But I have a feeling I'm being really stupid here for a moment. Let's. I hope we don't. I would love to finish this right now. Let's. The obvious point is this: you want to apply a Stokes theorem for the cube, right? So you want to apply a Stokes theorem for the cube, and I'm not sure. I don't think I have to do all of this. Do I have to do all of this? No, I think what I did here is not necessary. No. So, I beg your pardon. It was not, it's true what I said, but I think it's just not necessary, okay? So, forget Leibniz. I thought I had to do this here. No, I don't think so. Okay. Sum. So I need, that commutes with D. This I of course want to do, right? D of phi star gamma I alpha. Okay? And integral over the cube, and now I apply Stokes' theorem on the cube. So what I was doing there was completely unnecessary applying Leibniz, right? I apply Stokes' theorem on the cube. Now, there are two types of open sets to consider. There's the open set in the middle set. Yeah. So let's call these open sets UI in the middle. And let's call these things here UI on the boundary. Okay, what do I get on the middle open sets? I'm applying Stokes' theorem here now on W. These things on the middle open sets are 0 on the boundary. right? So what we get here is the sum over, if you don't mind, I will write CI boundary of this stuff, of D gamma I. And now, what contribution do I have on those things? Here I get no contribution from Stokes in the cube. Here I get the boundary contribution. So I simply, the integral's still here, okay? So what I get here is, of course, the integral over the boundary, the sum of the integrals over the boundaries of these of the relevant ui's of gamma I alpha, and this is then the integral of alpha over the boundary.
Professor, can you explain again why ui integrate over ui is 0?
Which one?
I mean,
The middle one.
yeah, the middle one.
The middle ui. Yes, because this form, this thing here, has compact support in ui. So it's 0 in the boundary, everywhere.
Oh,
Right?
But are you already applying the Stokes?
I'm applying, where am I applying? To bring this from here to here, I apply Stokes to the middle ones and say they don't contribute at all.
But I think it's like you are trying to prove Stokes theorem using the Stokes theorem, is it?
Of course,
How do you-
I use Stokes theorem for the cube to prove Stokes theorem for anything.
Okay.
And I use Stokes theorem for the cube 2 times, once for the middle coverings, because there are no boundary terms at all, and Stokes theorem says the integral is 0. Right? And then I use it again for the boundary terms and get the boundary contribution. Right? They're going to get mad at me for going over, but I mean, you understand, this piece here, the form that I'm discussing, if this piece for a cube goes here, the support of the form is here. Yeah? So, you see, you don't get any contribution here, you only get the contribution here, which is the contribution here. And that's what this is the last, maybe I should circle this with orange, because this is the last contribution in this last step. I applied it twice here to kill all the middle terms, and then I just apply it again to get the right boundary term. And as you say, I'm proving Stokes with Stokes. But Stokes for anything, and using Stokes for cubes. And Stokes for cubes is just Fubini theorem or some direct calculation. Okay. And you're absolutely right in estimating this is trivial. It is absolutely trivial and formal, except for one point, that the integral is well defined. As soon as you have the integral well defined, you're finished. Okay, I'm maybe people will be mad.